Okay, so try to reduce three sat to independent set, huh? So let's remind ourselves: independent set. We have a graph of G and an integer k, and we want to simply know if there is an independent set in G of size k. That's all we want to know. So as a result, this was our motivating example, and an independent set was we had a 3-vertex independent set. Okay, it isn't our only independent set, but it is the maximum size independent set. I want to say, yep, maximum size independent set. Okay, so question is, how do we reduce? So question is, how do we reduce? How to reduce 3 sat to independent set. Okay, so let's recall the reduction diagram. We have the algorithm for, we want to show 3 sat reduces to independent set. So we have the algorithm for 3 sat here, AX. We have a 3 sat formula here. We have a reduction, and we have the algorithm for independent set here. We have yes, no, and we have the inputs to independent set. So we have 2 inputs to independent set: a graph G, that's the encoding for G, and K. We'll do that encoding also. Okay, so the question really is, how do we transform this stat formula into a graph? Okay, and how do we transform this formula into a graph and choose K such that if this formula is satisfiable, then this graph has a independent set of size K, and if this formula is not satisfiable, then this graph does not have an independent set of size K. That's what we need to do with our reductions. Okay, so what do we do in this case? We need to find a way to assign 0, 1 to variables such that the formula evaluates true if each clause evaluates to true. Okay, so before I say that, let me backtrack a bit and say, let's think about the SAT formula, the 3 SAT formula, I should say, a little bit. So how do we find satisfying assignments with the simple SAT formulas in the beginning of the lectures? What we did was simply look at the clauses and then make assignments to the variables such that we just picked one of the variables in each clause and assigned that literal to be true. We assigned the variable to whatever value so that the literal was true. And then we just said, okay, now that I have at least one assignment, one of those literals is true, then I can move on to the next clause, right? And hopefully I could keep assigning values to variables so that I could make the next clause true without interfering with the variable assignment that I already did. Okay, so we simply pick a variable, literal, from each clause and find the truth assignment to make all of them true. So we're just picking a literal from each clause. So how does that relate to independent set? That's the question. Well, let's play around with the idea a little bit. Okay, let's say we have a particular 3 sat formula and we need to transform it into a graph. Okay, so let's transform it into a graph, and let's say for each literal we have a node in the graph. Okay, for each literal we designate we add a node to the graph, each literal. Okay, what do we do next? Well, we need a way to designate that there are 3 literals per clause, so maybe we should just add edges between the literals. Okay. Okay, this gives us groups of three, right? Each of the connected three components, each of the connected three literals designates a clause, right? So what I need to do, what I did before, really I need to just find one literal from each clause that evaluates to true. I mean, I just need to pick one literal from each clause that I could assign to true. Okay? So in each of these clauses, I mean, yes, these are connected together, so I can't have an independent set of size 9. But even from the SAT formula, I just need, if there are m clauses, for these m clauses, I just need m literals to be true, right? I just need m literals to be true. So what do? I just set k equal to m. I say if there is an independent set of size m, that means the independent set chose one literal from every clause, because it can't choose two literals from a clause because they're all connected to each other, and that wouldn't be an independent set. So the only way for there to be a size m independent set is if the algorithm for independent set chooses one literal from each clause. Right? Okay, we're on this sort of right track, but there is a problem. What's the problem? What if the algorithm for independent set chooses not x1 and x1? That's not possible in the SAT formula, right? x1 is a variable. x1 could be either 0 or 1. We can't say not x1 evaluates to true and x1 evaluates to true at the same time, right? So we have to stop the independent set algorithm from selecting both a variable and not its variable. So what do we do in that case? We simply add edges between a variable and not its variable. Okay? And because of that, now the independent set variable cannot choose both x1 and not x1. Okay? But it could still choose x2 and x2, which is fine. This would simply mean we assigned x2 to be true. But it can't also true not x2. So we could effectively say choose x2, this would be true, and x1. Or we could choose x2, x1, and x4. This would also satisfy the equation. But the point is that if there is an independent set of at least m, where m is the number of clauses, then that means that there must be some set of literals that A, don't conflict with each other, i.e. don't conflict with each other, and that you could use to designate a truth assignment that satisfies this equation, the original SAT formula. Okay? So basically the reduction is simply we take a SAT formula in, we create a graph, and therefore we create a graph, and then if there is a algorithm that solves independent set, then it will also solve SAT, right? But we know SAT is a hard problem, so then we know that independent set must not have an algorithm that's hard, as far as we know. So this right here shows independent set is NP hard because it's reduced from 3SAT, which is reduced from SAT, which is reduced from every other NP problem, thanks to the Cook-Levin theorem. So we know it shows NP hard, and we know independent set is in NP because the certificate could be simply a subset of vertices, and the certifier is simply the check to make sure there's no edges between those vertices. So we know it's an NP, we know it's NP hard, and therefore what is independent set? Independent set is NP complete. Okay? So that is the first reduction. First mainstream reduction that we will do. And in the next lecture, we're just going to go through a couple more reductions for some other famous, for some other well-known NP complete problems. Okay, so that's it for today. Thanks for sticking with me, and I'll see you on the next one. Thanks.